but that only happens if we finish this and we finish the review. All right, so let me get started here. All right, use the Nernst equation to predict the spontaneity of the redox reaction shown below. So let's go ahead and do this and our last problem here. All right, the first thing I want you to recognize is that this is non-standard state. Okay, since it's non-standard state, okay, we're going to use the Nernst equation. All right, so that's that concentration, and then we have another concentration here, 0.15 molar. All right, so first things first, in the blue, I'll have cobalt go to cobalt plus 2. Okay, how many electrons and where do we put the electrons? How many electrons and where? It's going to be 2 electrons in the product side. Does everybody see that? Okay, yes, yes. Okay, everyone get that? Okay, I see some nods. Okay, very good. Is this oxidation or reduction? Okay, we lost 2 electrons, so losing 2 electrons is LEO. We lost 2 electrons, so that's oxidation. What happens, or where does oxidation occur? Very good, Allison. It occurs in the anode. And let's figure out the voltage associated with this. Anybody see cobalt, or am I just losing my mind?
0.31, but positive, right?
Here goes up on top, right? No, that's cobalt to cobalt plus 2. Maybe it's not here. Oh, here it is. I found it. Okay, wow. That's a hard one. Okay. Is this it?
Three ones. Or maybe I did it wrong.
I can't see from this angle. Okay. I can't see from this angle, so it's not 3-1, it's 2-8. Okay, but I can see it being 3-1 because it's... Okay, so make sure you line them up. That's a mistake I can make. Yeah, definitely, which I have made. But no, is it really minus 0.28? What is it?
Yeah.
Minus or positive?
Well, because it's flipped, it's positive.
Because it's flipped, it's positive. So we're going to call it positive 0.28 volts. All right, so that is that. Good job. And then we have iron. I'll do this in brown. Iron plus 2 going to Fe solid. Okay, so I'll do this in red. How many electrons and where? 2 on the reactant side. Is this the cathode or the anode? Well, no, if this is the anode, then what does this have to be? Okay, just by default, it has to be the cathode. Okay, because you can't, one needs to be the anode, the other needs to be the cathode. And what do we see for here? Fe, go to Fe solid. I see it right here. What is that, 0.44 or 0.74 negative?
Negative 0.4.
Negative 0.44. Negative 0.44. All right, this is how many electron transfer reaction? This is a 2 electron transfer reaction. Very nice. Okay, this is a 2 electron transfer reaction. And then, so we don't need to multiply anything, so 2e minus 2e minus. So have cobalt solid plus Fe plus 2. Goes to Fe solid plus cobalt plus 2. And this is E cell. What is E cell here? We're going to add those two together, and what will we get? What's positive 0.28 minus 0.44? Positive 0.28 minus 0.4. You guys can't do this in your head. Simple subtraction. Well, neither can I. So 0.28 minus 0.44 minus 0.16 volts. Minus 0.16 volts. That looks like it's non-spontaneous, okay, in standard state. But this is not, okay, once again, this is not standard state. This is 1.94 molar Fe plus 2 and 0.15 molar cobalt plus 2. So we're going to use the Nernst equation. I'll give you this on the exam. Let me search for it here. Where are you, Nernst equation? Hiding from me? No, I got you. Alright, so the Nernst equation is this. It's E cell, let's see, equals E standard state cell minus 0.0257 volts divided by N. What is N here? 2 natural log of Q. Okay, so this Q is going to be the concentration of products over reactants. I'll put this in red. All right, are we ready to plug everything in? All right, E cell here is minus 0.16 volts. Minus 0.0257 volts. Divided by 2 natural log of cobalt plus 2, 0.15 volts, 0.15 molar, divided by Fe plus 2, 1.94. Right, can we do this on our calculator? Together, let's see what we get here. 0.15 divided by 1.94, natural log of that, times a minus, okay, times a minus, negative 0.0257, divided by 2, plus a minus. Everyone see here? Plus a minus 0.16. Did you get minus 0.13 volts? Yes? No? Okay, let me try that again. Natural log 0.15 divided by 1.94. Okay, natural log that. Okay, times a negative 0.0257. Divided by 2. Okay, plus a negative 0.16. I'm getting negative 0.13 volts again. Is that right? I got it twice, so. Negative 0.13 volts. I got it twice, so is that what you got? Okay, all I need is 1%. Yeah. Negative 0.13 volts. Okay. This is E cell. Okay, we can do it together. If you didn't get that.
I just wrote it down wrong. That's
Oh, okay. So you got it right.
E cell and
Okay. So So make sure you know how to do this on your calculator. It's definitely something that I can mess up on, so anybody can. Calculator error. And so this is also non-spontaneous, just like a standard state condition. All right. All right, let's do our last problem here. It's the exact same type of thing. So let's go ahead and do that, and that will end the course for us. All right. So how will we do this? Okay, it's a different way of looking at the same problem, but they're using galvanic cell notation. All right, so in galvanic cell notation, it's going to be the anode couple. Okay, we're going to draw two lines here that represents a salt bridge. And then we will have a cathode couple. All right, so here this represents our anode. We'll do that in this color here, blue. Okay. So we have Al. No, we'll do it in a different color. Al solid goes to Al plus 3. Okay, how many electrons and where should they go? This is the anode, so in the anode the electrons go on the product side because anode is the site of oxidation. Furthermore, lose electrons, oxidation. So we're going to put 3 electrons here. This is the anode. And what is this on our sheet here? Okay, so this is what positive 1.66. Yep. So positive 1.66 volts. And then let's do the cathode couple here. We have copper plus 2 goes to copper solid. And this is obviously going to be the cathode. And then copper plus 2. Here I see it here. We're not going to change the sign. And are you guys getting positive 0.34 volts? Yeah, positive 0.34 volts. Going once, going twice. Yes. Okay, I'm guessing it's positive 0.34 volts. All right, so we gotta multiply things out to cancel out the electrons. I'm gonna multiply the top one by what number? 2. Okay. Along those lines, I'm gonna multiply the bottom number by 3. How many electrons are being transferred in this reaction? This is a 6 electron transfer reaction. If I multiply this by 2, what does this number become? Remember, we never change the number. The only thing we change is the sign. Okay, and then we have 6 electrons here, plus 3 is copper plus 2, goes to 3 copper solid. This is positive 0.34 volts. And I'm getting 2 Al solid plus 3 copper plus 2 aqueous goes to 3 Cu solid plus 2 Al plus 3 aqueous. And this is coming about to 2 volts. Okay, nice. 2-volt battery between aluminum and copper. And then we'll use the Nernst equation now to figure out what is the actual voltage at this concentration, 0.15 molar, and that concentration, 0.025 molar. Okay, so actually let's just move it all the way up here and do it. Okay, what is n here? 6. Natural log of Al plus 3 squared. Okay, we need to square that. Actually, let me just do that at the bottom here. I just don't want to confuse everyone. Let's do it at the top. N is 6. Natural log of Q. Okay, products over reactants. Al plus 3, that gets the square, divided by Cu plus 2, that gets the cubed. Okay. Alright, let's plug in our numbers here. E cell is going to be 2 volts minus 0.0257 divided by 6. Natural log Al plus 3, if I'm looking up above, I'm getting it as 0.15. Don't forget to square it now. Divided by copper plus 2, which is 0.025. Okay, don't forget to cube it. Let's see if we can do this on our calculator, see if our answers connect. Alright, so 0.15 squared divided by 0.025 cubed. That's what I'm getting, 1440. I'll natural log that answer. Times a minus. Look at the sign here. Times a minus 0.0257. So times negative 0.0257. Okay, divided by 6. And plus 2 volts. Plus 2 volts. 1.97 volts. Yes. Okay, got 2 nods, so 1.97 volts. It too is spontaneous, so it favors the products. Right. So there you have it. Okay, we finished the course, so you can give yourselves a round of applause. And let's go ahead and quickly jump to the review here. These are some practice problems. You need a copy of this. Get a copy. Next test. Next test. All right. Have a good one. Take care. And there should be 5 pages here.
Perfect timing. Clearly go.
So you can watch the video, and you have this now. You can do it and then compare it to what we get. Yeah.
Watch
All right, so this is a majority of the test. Not all of it, but a majority of the exam. Okay, so all right, so there's a lot of multiple choice in the test. So it's about 35 points, so about 15 to 16 points are going to be multiple choice short answer questions like this. All right, so we can go through this kind of fast. So a gas that goes into solid, the change in entropy is, okay, a gas going to solid. Would that be more order or more disorder? Okay, so more order implies your change will be positive or negative. Okay, negative. All right, so delta S will be negative if there's more order. Okay, more disorder or less order. Okay, that is entropy. Okay. Delta S would be positive. Excuse me. Right, how about this one? Oxidation occurs in what part of the galvanic cell? Okay, you want to remember Leo Gur. Okay, Leo Gur. And another one you want to remember is red cat eats an ox. Yeah, red cat eats an ox. So oxidation occurs at the anode. Okay, so this is the answer. Okay, red cat eats an ox. Reduction at cathode, anode oxidation. Leo lose electrons oxidation, which means electrons go into products. Gur means gain electrons. So if you gain electrons, it's part of the reactants. All right, what about reduction? Okay, this would be the opposite, right? So on the test, if there's reduction occurs where? Cathode, right? Reduction occurs in the cathode. All right, for the half-life of the reaction, okay, we have this equals to positive 2.87 volts. All right, and is this oxidation or reduction? Okay, reduction, because this has gained 2 electrons. Okay, what do they do here? They multiplied by 3. Okay, if you multiply it by 3, what will this number be? The same. So the numbers in this table that bring this to the exam, the numbers in this table never change. The only thing that changes is the sign. All right, for a reaction to be spontaneous, E cell would be what? Positive, negative, have a K less than 1. Okay, remember the units of this are in volts. So if you have positive voltage, what will that mean? It favors the product side. So for a reaction to be spontaneous, what will the E cell be? Positive. Okay, so if you want something to favor the products, you should know this. Okay? All of these 3 things favor products. Okay, if you want a reaction to favor the products, the E cell, which is the anode and the cathode, must be positive. So that's a positive voltage. Okay? All our batteries run on positive voltage, isn't it? If you're talking about equilibrium, the equilibrium constant should be very large. Okay, remember, if you have $1 million, you're moving forward. So if a reaction has an equilibrium constant millions, it means it's moving forward, facing the products. And then in terms of energetics, the delta G, whether it's in standard state or non-standard state, okay, it must be negative. Okay, negative. Okay, all of these aspects favor a reaction that is going to move forward and favor the right-hand side. Okay. All right, so make sure you remember those 3 things. This has to do with electrochemistry, this has to do with equilibrium, and this has to do with energetics. Okay, we just answered this. If K is positive and E cell is positive, then which way will the reaction favor? Product side or reactant side? Product or reactant? Or none of the above? Okay. Product side. Okay, product side, very good. Okay, what happens if K is small, or I should say, if K is less than 1 and E cell is negative? Okay, this is exactly the opposite situation where you would have reactants favored. Okay. All right. A reducing agent. Okay, what does a reducing agent do? Okay, it is the agent that causes your reduction. I am a reducing agent means I reduce you, I reduce you, I reduce you, I reduce you. So if I reduce all of you, what will I eventually become? Oxidized. Okay, I will eventually become oxidized. Okay, what if it's asking for an oxidizing agent? Okay, I'm an oxidizing agent. Okay, I oxidize you, I oxidize you, I oxidize you, I oxidize you. What do I become? Reduced. Okay, it's just that I may, if I'm an oxidizing agent, I may reduce you more than I may reduce you, Leslie, more. Okay, so that's where we have the activity series. The activity series, which is this table, tells us which one is likely to reduce the other. See, I'm an oxidizing agent. I'm going to oxidize you or you, but which one would I oxidize better? Okay, so that's where we use the table here. But yes, if I'm an oxidizing agent, I oxidize you, but I myself get reduced. Okay, so let's just write an oxidizing agent gets reduced.
What might that look like? Like in our lab, if something's a reducing agent, how would that look like practically?
In that lab, it turned from yellow to blue.
So it's like a color change.
Yeah, color change or a voltage change. Yeah. Usually it's a voltage change in the voltage. Yeah, if it becomes more negative, okay, then it's a good reducing agent. If it's becoming more and more positive, then it's a good oxidizing agent. Okay, but in the lab, when you were testing whether it gets, you were testing all these 4 different things as reducing agents, or these 4 other things as oxidizing agents. You're looking for color change between yellow to blue or blue to yellow. All right, this is a good segue to this. Okay, beryllium plus 2 will cause the reduction of Al plus 3 to Al. Beryllium plus 2. Where is that? I don't see beryllium here. Okay, will cause the reduction of Al plus 3 to Al. Will cause the reduction. What is reduction? It means cause the reduction of Al plus 3 to Al. So everything up above is reduction. Al plus 3 to Al will cause the reduction of Al plus 3 to Al. So do you think this is true or false? All right, so will beryllium cause the reduction of Al plus 3 to Al? The answer is yes. Okay, remember you pick one and then everything above it stays the same. The one that you choose gets flipped. Okay, so yes. The answer is yes.
So the more positive the voltage gets, it's getting more reduced.
You want an E cell to be positive. That's where the reaction will happen. If it's becoming more positive, it's actually getting more reduced. You're right. Yes. Let me just do that here. Okay, as it's getting more and more and more and more positive, okay, you're seeing the reduction is happening better and better and better. Yeah, here, more positive means it's good at being an oxidizing agent. All right, Na plus will cause the oxidation of Br minus to Br2. Okay, Na plus will cause the what? Oxidation. Will this cause the, what will it cause the oxidation of? Okay, it will cause the oxidation of calcium to calcium plus 2. It will cause the oxidation of strontium to strontium plus 2. It will cause the oxidation of barium to barium plus 2. It will cause the oxidation of potassium to potassium plus, and lithium to lithium plus. So you see bromine, Br anywhere there? Okay, so is this true or false? Okay. Zinc will cause the reduction of cadmium plus 2 to cadmium. Zinc will cause the reduction of cadmium plus 2 to cadmium. Where is zinc? The zinc solid, it says. Zinc solid is causing the reduction of cadmium plus 2 to cadmium. Do you think that's true? I think that's true, okay? Because you keep everything above it the same, this one gets flipped. So when zinc causes cadmium plus 2 to get reduced to cadmium solid, it itself gets oxidized to zinc plus 2. I believe the answer to this is true. Okay, right? I agree. Okay. Lithium is most likely to get reduced in the standard reduction potential table. Is that true or false? False. It's most likely to get what? Oxidized, because when it gets oxidized, it will give 3.05 voltage, or 3.05 potential, and that's energy. So that's false. Okay, which is a stronger oxidizing agent? Iron plus 3 at positive 0.77 volts, or copper plus 2 at positive 0.15 volts. So a reducing agent is an oxidizing agent gets reduced, right? Remember? It's the one that's getting reduced. So looking at our table, more positive or more negative? Okay, so you're looking at something that's more positive. So which is more positive, Fe plus 2 or copper plus 2? Okay, so something that's getting reduced, we're associating it with a more positive voltage, and that's going to be Fe plus 3. All right, which is a stronger oxidizing agent. The oxidizing agent gets reduced. And looking at our table here, okay, the more reduced you get, the more positive you become. Okay, so F2 plus 2 electrons goes to 2F minus is the most positive at 2.87 volts, and that's the best oxidizing agent. It gets reduced the best and oxidizes everything below it. Everything in this list below it gets oxidized. So the more positive, the better it is as an oxidizing agent. Okay, and you know, like I said before, this can flip and oxidize everything below it in this list. All right, let's move on to page 3 here. Right, so these are sample problems from your test, so your test will be just like this. Okay, I just changed the numbers here and there, the reaction. So sample problem number 12. Write the galvanic cell notation for the following reaction and calculate the E cell. Determine if the reaction is spontaneous or non-spontaneous. So we have here chromium solid going to Cr plus 3 aqueous. Okay, how many electrons and where? 3 on the product side. Is this oxidation or reduction? Okay, and what is the voltage associated with this? Chromium to chromium plus 3. And I am seeing this as I found it. I can't see this. I can't line them up. Is it negative 0.74? Yes, thank you. Okay. But we need to flip it, right? Or do we? Yeah, positive 0.74 volts. Okay, so this is the anode. The cathode is nickel plus 2 going to nickel. Nickel plus 2 going to nickel solid. Okay, how many electrons and where? 2 on the product's reactant side. This has to be the cathode if the other one is the anode. And what do you see here for their voltage? Is it listed? I see it. And I see it as negative 0.25 volts. Okay, we keep it the same. We do not alter it. All right, how many electrons are being transferred in this reaction? This is a 6 electron transfer reaction. First thing, I'm going to multiply this top one by 2, and I'm going to multiply the bottom one by 3. This becomes 2Cr solid, goes to 2Cr plus 3 plus 6 electrons. Okay, we do not change this. It's going to be positive 0.74 volts. And then we'll do the same thing here. This is, let's do that in red, 6 electrons here, plus 3, nickel plus 2 aqueous, goes to 3 nickel solid. Okay, 3 nickel solid. This is minus 0.25 volts. And this is going to be 9.49 volts positive. And then my net is going to be, well, my net's going to be this. Okay. When I add them up. Okay, so this is E cell. Standard state. All right, so what is our answer for this problem? Okay, the answer to this problem is positive 0.49 volts. And is this spontaneous or non-spontaneous? Okay, positive voltage, spontaneous, favors the products. All right, same thing with this one. Let's go ahead and do it. Okay, I'll ignore the coefficients. Okay, here we have Al solid. Oh, we forgot. Okay, we forgot. Write the galvanic cell notation. So how are we going to write the galvanic cell notation on the test? Okay, what comes first? The anode. So the anode is Cr solid. Okay, you're going to draw one line. Cr plus 3. Don't forget this on the exam. Okay, what is the salt bridge? 2 lines. And then the cathode couple, which is nickel plus 2. We draw one line down here, nickel solid. Okay. So that's what you want to write because this is the galvanic cell notation. Alright, we'll do the galvanic cell notation for this one as well. We have Al solid going to Al plus 3. Okay, we have 3 electrons. This looks to be the same as the previous one. What is this here? Al going to Al plus 3. everyone see that here? Oh, I'm losing my mind. Oh, I find it. Okay, I found it. I found it. And I lost it. I found it. Okay. Negative 1.66, but we're going to flip it and make it positive 1.66 volts. And then we have beryllium going to beryllium solid. Okay, this is two electrons on the product side, and beryllium here is negative 1.85 volts. Okay. Okay, remember this is the cathode. Nope, this is the anode up above, and this is the cathode down below. Okay, so it looks to me like, just like the previous problem above, this is going to be a 6 electron transfer reaction. So we'll multiply the top one by 2, and then the bottom one by 3. And then we will finish this up here as 2Al solid plus Be plus 2 aqueous goes to Be solid. 3Be plus 2 goes to 3Be solid plus 2Al plus 3. We multiply the top one by 2 to get this to 6 electrons, and then we multiply the bottom by 3 to get this to 6 electrons. So the 6 electrons cancel.
But is this on the question or on the given reaction?
Yeah, I already have. Yeah. We generated the given reaction. All I did was split this up into the anode and cathode and regenerated it back up here. You don't, yeah, this is the balanced equation. So all I did was take this and then, like I said, I split it into the cathode and anode, or anode and cathode. And then when I multiplied it by 2, I get the 2 back here. When I multiplied it by 3, I get the 3 back here. So in case this confuses you, these coefficients, if you don't want to, if you don't want to ignore them, because you saw how I ignored them, you can also do it like this. Okay, we have 2Al solid goes to 2Al plus 3. First of all, the 2's cancel, but okay, the 2's will cancel, but let's say you don't cancel the 2's. Okay, how many electrons and where will you put them? Okay, you'll put 6 electrons here. Okay, because 2 times 3 is 6. Okay, this is still my plus 1.66 volts, because if the multiplying or that numbers, you never change the numbers, you just change the sign. Okay. Okay, this is 3Be plus 2 going to 3Be solid. 3Be plus 2 aqueous goes to 3Be solid. Okay, how many electrons and where should I put them? Okay, 3 times 2 is positive 6. So I'm going to put 6 electrons, 6E minus here. And like I said, these numbers never change. Just the sign. So this is a 6 electron transfer reaction. You're still going to get that. So you can keep the 2's or you can remove the 2's, but but you'll get them back. You'll get back the 2s and the 3s when you balance it. Or you can keep the 2s and the 3s and just realize it's going to be 6 electrons here. All right, minus 1.85 plus 1.66, what is that on our calculator? Point what? 0.19 volts. And is this non-spontaneous or spontaneous? So the answer to the overall test question is this is non-spontaneous. And what's the anode couple? Al, we're going to draw one line as Al plus 3. Salta bridge, Be plus 2. Aqueous, one line, the cathode couple, Be solid. Okay, if you want to be more thorough, I think you did this, Asia. If you want to be more thorough, you can do 2Al solid. Okay, and that's going to 2Al plus 3. Salt bridge is 2 lines. 3Be plus 2, this is the cathode couple. Okay, one line, and then 3Be solid. So this is probably a better answer because it takes into account the stoichiometry. All right, so we'll finish the rest of this on Friday.